top key problems, which involve finding the key smallest or largest elements in the collection of elements. There is a wide range of this kind of task. It's one of the popular, but we will cover two more, which is also very popular during the interview, and which is not falling under top key problems. But all the top key problems usually solved easily with Heap. Yeah, so Heap properties. A heap is specialized tree-based data structure that satisfy the heap property, which could be max heap, parents greater than children, largest at the root, and min heap, parent is less than children and smallest at the root. This is the example of min heap. Here's the parent, it's our root, it's 1. And this structure is called tree. If there is someone who is not familiar with tree and heap concept at all, and first time hearing it, you can just up your hand. Okay, cool. It's nice. So seems everyone on the same page. Okay. Otherwise, don't hesitate ask any questions because it is quite a complex data structure. So, for example, we can value, this is the heap. It's usually represented as an array, but underneath it is actually tree. Max heap and min heap, somewhere down I put the examples. This is our max heap, and this is our min heap. I hope it's clear. So we're starting in max heap, we're starting from biggest element, and we go all the way down, and on our leaf, there is the smallest elements. The opposite for min heap, root element is the smallest one, and at the leaf, we have the biggest one. Okay. So the element correspond to the level order traverse of binary tree. So this is this kind of concept we will cover in deep in our next session. What is the level order of traverse and what is the binary tree? The root of the binary tree is stored at the index 0. It is left and right children are stored at the index 1 and 2 respectively, and so on. So what does it mean? There is our root. If you will take a look, there is will be next will be our children's, which is 2 and 4. Next will be children's of this parent. It will be 5 and 8, and it will 6 and 9. 6 and 9. What does it mean level traverse? That we're starting like this. We travel 3 this way. This is a level order traverse of binary tree. Okay. There is, I added these concepts for now, but we are not going to use it as a part of heap. I saw that it is actually meta when we are working with tree problems, and there is this concept how to find the indexes of the left child and right child and parent child is actually needed. I left it here, but I keep in mind that next lectures when I will prepare, I will try to include task. LeetCode task on this concept as well. But today it's just for like bonus knowledge, which is we are not going to use. I don't remember that in any heap problem I ever used this concept at all. So just to cover, what does it mean? So for any nodes at index 0, left child you can find by this formula, and right child you can find by this formula, and parent you can find by this formula. So if you take took a look at the example, for example, now we have index, which is 2. The left child at the index will be found by this formula, which is at the 5. So you can see this is the left child of this index. And at the 6 index, 1 second. So index 2, it is this 4, 1 element, which is this index 2, and the element is 4. And we can find by this formula of his child, which is 6, and which is will be pointed at the index 5 and index 6. So, and yes, you can find parent of this index, of this element, the index 2, which is will be 1. This is the parent, and this his children's. Moving. So heap operations. In different languages, it's different. So that's what I opened for myself during preparing the lecture. In Python and Java, it's slightly different. Yeah, folks, you can, if you are writing on different languages, and if I'm missing something here, you can add. I was covering this lecture for Python and Java. So heap operation, it's insert, pick, extract, means pop, remove, or poll, depend on language. There is different methods which is you will use, and heapify. So what is notable about this data structure? If we compare stack, it was all the operation was done in constant time. But for heap, all this operation will be in log n, a part of peak, because peak is just taking the top element at the heap. And heapify, it's actually just to build heap. Means your, what does mean heapify? You are taking your array or list, unsorted data structure, and you're building actually heap. As I mentioned, heap will be built into tree. And why we having this operation? Because when we will insert, I will cover it here. Yeah, we can actually go. So why does push take log at n? N here it is the high of the tree. Heap a completely binary tree, which means that all levels of the tree are fully filled except for the last level, which is filled from the left to right. This is the valid of fully filled binary tree, and this is not because it should be here, should be children, and not here. And all the levels is balance. That's why we can predict that any operation will take all again or 10, where n it is as a high of the binary tree. Means it's self-balanced. Whatever you're doing modification with your heap, like insert or add, what it will happen underneath, it will find the right place for your children. If it's so the less costly operation, it will be just to insert underleaf. But for example, you're having here 1, and you're having here 2, and you need insert 3. So basically, you need to rebalance your tree in order to find the right place for the free elements. That's why it's in the worst case, insert and delete operation will take log n in time complexity. So this is the example. 1 second. It's the important property to keep. Yeah. Suppose you insert 1 into this min heap. Yeah. So this is the example of the inserting elements into heap. So we have initially this heap, and we're trying to insert 1. What will happen in this case? First, we will add underneath, I mean at the end, but it will be rebalancing underneath. So basically, we will swap with 5 first, then we will swap with 3, and then we will swap with 2. And eventually, 1 will be our new root. Yes, it stayed the balance, as I mentioned. Inserting required moving up at most log at n levels, and then push and insert. Yes, so basically it's everything what I just told. So this is important to understand from where this time complexity came from. Okay, this is max heap example. Now I finished, I believe, with terminologies. Now I'm going to implementation. Yes. So just to sum up, before I will come to the implementation, we have heap, which is min heap and max heap. Min heap means at the root the smallest element. Max heap means at the root the largest element. Insert and remove operation taking log n operation. It is a balanced tree underneath. Means and it is our high. And peak will take constant time, and heapify, it is the operation where you just putting your raw data structure and you're trying to build heap. So this is what basically all the concepts for this lesson today. Now, I was surprised that Python provide built-in module called heap queue, but it is by default min heap. So I put some code here for visualization purpose. What so heapify, we convert array. This is our array structure. We convert it to the heap. Next, at the heap, push 0 will be and pick element. So there will be a 0 element at the top. Min element, it will return 0. Next, it will be 1. So it is interesting that max heap doesn't support it out of box in Python. In order to make max heap, to create max heap, we can negate the values in the list and then convert it into heap using the heapify function. Which is you have this array and you just negate all the values. That's how the max heap is built in Python, which is not the same like we have in Java. So in Java for heap, we're using priority queue. By default, it's min heap. If it looks like this, so it will be min heap. But if you want to make max heap, you just need to provide the reverse order to tell exactly your priority queue, how to order the elements into your data structure, and then it will be max heap. So this is kind of things which is because will be task on the max heap. You should understand how to do it in the Python if you don't know. For me, it was something new, which is I learned. Yeah, and in Java, you're using just priority queue with different, you just explicitly tell, is it min heap or it is max heap. So I'm done at this point with lecture. Any questions before I will move to the our first task? Okay, cool. Thank you, folks. So top k frequent words. Given an array of string word and an integer k, return the k most frequent strings. Return the answer sorted by frequency from highest to lowest. Sort the words with the same frequency by their lexicographical order. This is adding complexity to the task because we just we're not just returning the most frequent words, but if there is they are equal, For example, I believe in this case, I and Love were meeting twice. They both have frequency of 2, and we need to preserve lexicographical order. So, from the description, is it clear what has been asked? Okay, cool. I will tell you in advance, folks. There is usually for this kind of task, there is many options how you can solve. Mean heap, I will just tell in advance because I think it will be easier for you to follow next. Mean heap, you can solve it with max heap. We will solve it with max heap. We will also solve it today with the sort, and eventually we will sort this with mean heap. It will add a slight benefit, but it is not like we dramatically will optimize our solution. The most optimal solution for this one, it is actually sorting. But it is very advanced, and it's usually very difficult during the interview to implement it. I will drop on the Slack because I don't think that we will cover this sorting during any our lecture. And usually what during interview is happening, you acknowledge regarding this particular task, because top K frequency is can be solved in different way. You are just explaining all the options. Usually you agree on the mean heap, but it's nice to tell that you know the sorting, and you are saying like, yes, I know the sorting. This will bring this time complexity and this space complexity. But it is very difficult to implement during the interview. So, and usually you agreed with the interview to come up with to implement the mean heap solution for this kind of task. So let's get started. Two main challenges for this one task: identifying the key most frequent string, sorting those string by frequency, and then lexicographically. The brute force approach will be here, as we need the most frequent keywords to find with words of high frequency. We just need to sort all words by their frequency and return the first keywords. Notice that sorting order is first by frequency and then lexicographically. According to the requirements of the problem, it will be all the same step for all the approaches which we will discuss. How we count the frequency of each word and store the record by hash map. So basically, what does it mean? Very first step will be to walk through your input data and count the frequency. For this reason, we will use a hash map, where the key will be word and value will be frequency. This is very common approach, and usually that's how it used. Once you need to count frequency, so it is 100% will be used hash map in this case. Define the sorting order as what problem indicates by frequency from high to low, and then from lexicographically smaller. Once large ones we meet time frequency and sort the entire list of all words. Only return the first keywords at the return result. So this will be our brute force solution. These first steps, when we're taking our input data of words, we just walk through all the words. We're putting words and we're counting how frequent we saw this element. It will be our O10 time complexity here. Then we're adding all the candidates here. So we did the frequency, and then we are sorting our candidates. Yeah. List sort candidates. 1 second. Get equal. We went compare case set. I think there is mistake because we are putting here, I will double check it, because we're putting here just words without frequency. But then we're actually saying that we want to sort our collection. CNT. Okay. So yeah, it's okay. It will work because what we're saying here. So we're taking yeah. Okay. So it will work. This is this probably Java specific. We are building our list of candidates, and then we are trying to sort them. What we are saying, how we want to sort. First, if the frequency is the equal, means if you actually saw your elements the same amount, the same amount of time, like I explained it, I and love in our example, it was 2 times. Then you compare them by lexicographical order. That's how you will sort elements in this list. And at the end, you will just return sublist, which will take first key elements from this list and will build the sublist here. So this is brute force solution. Is it clear what we just did here? So we just created hash map, then we created a list of data, and we just sort them the way we were asked. Okay, moving next. This will be our time complexity here and space complexity. Next will be, because here we have some like hint. By frequency from high to low, we can think, okay, maybe I can solve it with max heap because we need travel from high to low. Oops. So if we put all numbers into max heap, the top elements of the heap must be the max value of the all numbers in the heap. So instead of sorting all unique words, we only need to pop the word with the max frequency from max heap k times. The same first step when we walk through all these elements, we're building our hash map. Then we are creating our priority queue. This is how it's done in Java. Here we are building with custom sorting our max heap. So basically, it's the same rules for sorting, which is I put here. So first we are sorting them by frequency, and if frequency is equal, then we are asking to sort them lexicographically. Then we are adding to all these heap elements from our hash map. It will heapify them, as we discussed. This is basically a heapify method. And what needs to be done after all, you just you're just creating your output, and everything what is done, you are limited your for loop by k, and you're building your output. So you're returning the rest. This is how we can use max heap for this task. This is the solution for Python. I put it over here. Here is we negate frequency of our words. Yeah, for me, it's a little bit complicated to understand what is written on Python. I'm sure for you in Java, it's probably the same. So there is time complexity. We count the frequency. I explain it. I put the explanation. And space complexity will remain the same. Now, which is the most optimal solution out of the 3, it will be min heap. But it is, 1 second, how it will be the most optimal. Yeah. So basically, if our first solution was n log n, where we were in both of them, we were putting all the elements, then in this case, we actually will maintain our k ask. And this is reasonably short than to maintain all the data structure, because output could be huge, or it could be also a dynamic one, which is unbound, means your data structure, your elements is coming, and then you need to limit your time space complexity, and also you need to limit your time complexity. But in this case, we're not actually limiting space complexity because of this first step, where we anyway need to maintain a hash map. But time complexity will reduce. So it depends. It depends on the constraints of the task. It could seem like negligible optimization, but it depends on the input. If the input is huge, so then yes, you receive a huge benefit of using min heap. Let's walk through how we will apply min heap in this case. So approach 2 works best when the input is static, as I mentioned, meaning no new unique words will be added later. For top k problems where elements may be added dynamically, a common strategy is to use min heap of size k to keep track of the top k largest elements seen so far. Whenever a new element appears, we compare it with the smallest element in the heap top, because we will create min heap in this case, and the means on the top will be the mean one, the minimum one, to decide whether it's belong in the top k. Same step as in all three solutions. Next, we are building our min heap. We still need to provide some custom sorting here, because we need a lexicographical order here. Next, what we are doing, we're taking our frequency map, and we are adding words, and we're checking size. If it's more than k, then we are removing the elements from the top, which is mean one, will be out of the all elements there. I will show a diagram and it will be clear. Once you will build it, so you just need to save your result in the data structure which is required. So yeah, just step by step of our example. First, we will count the frequency. This is our min heap. It is empty for now. We're trying to add I2. So we are checking at this if we're trying to add LeetCode 1, and we're checking if the heap size is more than k. It's not. Then we're just adding the LeetCode here. Next, we are trying to add love word, and we're checking if the heap size is bigger. At the top currently will be our LeetCode. So this I just put it, but without order. So because it's min heap, means at the top will be LeetCode. We will remove LeetCode. No, first we will add. So we're trying to add love here. This is the iteration. Once we will add love on the top, we will have LeetCode. So basically, folks, this is what we have on the top. On the top, once we will add love and I, this is what we have on the min heap at all. At the top element will be our LeetCode 1. Here we compare the size, heap size with k, and it is bigger, means we will remove LeetCode from our top, and then we will try to add coding. We will add coding here. I think, yeah, it's missing. what will happen here? So assume we add coding on the top, we compare the heap size, and then we will just remove. We add first, and then we are removing it. So, and that's how in min heap there will be just at most k elements all the time. And at the end, you will just build the output format. So it's very straightforward algorithm. Build frequency, then you are creating your heap. You're walking through your map, trying to add words, and each step you're just maintaining the k size. That's it. If k size is beyond of k, then you're just removing it. That's how you know that all the time here only top k elements. So basically that's it on the top k problem. Any questions? Okay. Okay, moving then. This one of my favorite one. This is hard actually, folks. It's hard problem, and yeah, so you can proud of yourself once you will solve it because it's very interesting. It's a very hard problem, and a lot of companies, which is big funks or who is dealing with very selective process, they very like to ask this those kind of tasks. So let's tackle it. Find media from data stream. Design a data structure that support adding integer from a data stream and retrieving the media of all elements received at any point. So we need to implement add and get media method in this task, which means add an integer to the data structure and return the media of all integers so far. What is important to understand from this task that we have data stream, which is our input data is unbound and it will constantly coming new elements. You will add, and at some point you will need to figure it out what is your get media. So this is the example. For example, you're adding 3, you're adding 6, then you need to figure it out what is the media between them. And it will be 4.5. Then you again adding 1. And next you need to call and figure it out what is the media of this element, and it will be 3. Because underneath you not only, so they coming in unsorted order. But your data structure should support sorted order and should find the exact media at this point of time when this method will be called. So this is step by step. We're adding 3, then we're adding 6. Get media, it's called for 4.45. Then we're adding 1. 1 go to the beginning. And then you're calling method get media. It's free. So from the description, is it clear what asked? Okay, cool. Yeah. Yes, please ask.
Hi, thank you very much. Why its median is 3, last one? If so 3 plus 6 equal 9 and half of it 4.5, but here it is 10 and median is 3. I didn't understand, sorry.
No, the media of the elements means in this data stream, the media element is free. But in this element, because it was this one odd and this one even, So that's why in order to return the media, you should take 3 plus 6, and it will be 4.5 here. And this one, it is odd. You should return 3 in this case. So for example, here will be 4, and it will be 7. So you will still need to return 4.5.
Okay, thank you.
No? A good question. Yeah. The media is always found in the middle of sorted list of values. The challenge with this problem is that it is unclear how to keep all values sorted as new values arrive, since the values don't necessarily arrive in the sorted order, as I mentioned. A useful point to recognize is that we don't necessarily care if all the values are sorted. What really matters is that the media values are in the sorted position. But it is possible to position this value in the middle without maintaining a fully sorted list of values. If it is, we need to find a way to differentiate the media values from the rest. So, consider the elements below, which contain an even number of values arranged in sorted order. The two values used to calculate the media are highlighted in the middle. So I think I didn't make any mistake. So we have this data structure. This is our data structure. Now that we are clear on what is the media values means, so you just need to take one which is values in the middle of your data stream. Which, if you can take a look, so basically largest of the left half will be, and the smallest of the right half. I will put here. That's how we can find the media, two values used to calculate the media of this data stream. This is for even number. If we will take a look at this one, just 6. So then media value will be 4 in this case. We are not taking this one, or we're not taking this one. But for even numbers, so basically it will be left and right if we will take the half. When a list contains two media values, we can make the following observation. The first media is the largest element on the left half, and the second is the smallest on the right half. So if we had a way to split the data into two halves, with one half containing the smallest value and the other half containing the largest value, we would just need an efficient method to identify the largest value in the smallest half and the smallest value in the largest half. This is where heap comes into picture, folks. Yeah, is it clear? Observation and how we come up with this. Once you solve this task, you will remember it forever. So we're taking data stream. We need just to take. We notice this observation that data stream is just needs to be half, and on the left we have the largest one, and then the smallest we have the right half. So it means we can almost right away to think, okay, maybe I can use min heap and max heap in this task. I have someone who I believe raised a hand.
Yeah, thank you so much. Yeah, I just didn't understand the statement, like the largest value of the smaller half and the smallest value of the larger half.
Yeah.
Yeah.
So imagine you have this data stream. I don't want to say that it is data structure or input, because it's very important to understand that it is dynamic and all the time it will be changed. So for example, at some point of time, you have this data stream, you're adding elements and your elements is coming in different order. So for example, we are adding 2, then we are adding 3, then we are adding 8, then we want to add 1, just or 7 or 8. That's how elements is come. At some point, you just need to figure it out what is the media media values of your data stream. Means at this time your data stream should look like this. What is this? 1, 2,
3, 788.
788. Yeah.
Yeah.
And what is required to what is get media means? It is even. So get media means you need to find the value of what is the media of these two elements.
Yes.
And it will be 3 plus 7 divided on 2. It will be 5. That's what you need to answer in this task. To implement get media method.
Yeah.
And this one is add functions. So when you're adding, you're basically building somewhere you're maintaining your data stream, but you're not just simply maintaining your data stream, but yeah, as we mentioned, probably there should be kind of order. But if we simplify task to just find the get media, because we don't really much care about to sorting all the sorted to preserve all the order, because no one is asking us about media of these elements or these elements. We exactly know that we need to find the values of the media elements, which is in the middle of our data stream. In the middle. So this is some other hint which you can use. So for example, you have your data structure. You know that at this very moment you have 10 elements in your data structure. Means and you it is one thing which is you need just to achieve. It's that on your largest left half will be, so basically this should be ordered like this, from the smallest one to the biggest one, and the another half should be sorted in order from the minimum one to the largest one.
Yeah.
That's how you at any given time can answer on these questions. What is my media? If it's not still clear, you can ask questions. I will try to answer differently.
Yeah, I understood. But my question was like, usually whenever the even number elements are there inside the heap, then
Yes.
mostly the left half and the right half will be equal number of elements.
Say again.
Sorry. So usually when we have even number of elements,
Mm-hmm.
the left half of the heap and the right half of the heap will have equal number of elements.
Yes.
Then how can we tell that the largest of the smaller half, like both halves are equal? Sorry, am I? Yeah.
Equal size. Equal. It should be equal size. So what we will do now? This is for even numbers currently. What we will do now? We will maintain max heap here.
Yeah.
For this half, and we will maintain min heap for this half.
Okay, got it. Yeah, thank you so much.
So you just need at any point of time, yes, you need to maintain the exact size. It's not all your data stream.
Yeah.
You need to maintain, yes, but there will be some tweak how we are going to handle the odd numbers, because in case of the odd numbers, you just need to return one element. So I will cover it. So is it clear that it is won't be all the elements in one heap and another one? No, we're just dividing our stream on two parts, and we're maintaining the exact the equal size.
Yeah, understood. Thank you.
So if we had a way, to split the data into halves, okay, this is where heap is comes. We can use combination where top value represent the first media and the second will represent the media of populating. I'm just looking where I believe it will be here where I'm covering how we can handle odd numbers. Okay, now we will take this example, which is odd numbers. In case of odd numbers, we need to return just one element because this our media element. Populating the heaps. Before identifying how we populate each heap, it's useful to understand the behavior they must follow. Here's a couple of observations we can make. All values in left half must be less or equal to any value in right half. This is clear, right, folks? The two halves should contain an equal number of values, as we discussed, except when the total number of values is odd, in which case the left half has one more element as where I specified. So the idea is it is not strictly which halves to use. But in case of odd elements, we need to, at the beginning of implementing of algorithm, we need to define which half should contain these extra elements. And when we will adding these elements, we need exactly know who should be bigger, which part should be bigger, in order to keep this edge case. So usually it is when it is implementing, you're usually using left half, which is max heap, to keep these extra elements in case of odds. But it is not required. You can implement it the way, and your right half can keep it. So is it clear? What I'm trying to say, if there is even data stream, it's very obvious that all the parts should be equal. But as we know, there could be odd elements. At the beginning, we should keep in mind how to handle this edge case. And usually at the beginning of implementing of your algorithm, you decided which half should keep this extra element. Because because if you will take a look at the code, we all the time should keep checking the size of our halves. That's why it's very important. And that's how we can answer on these questions. So that's all algorithm is about. Just, yeah. So example. Which example I took? I took this one. I believe. So this is our heap. This is elements down on the heap because we have 3, so it could be in any order here. But on the top, it will be always 4. And here, for min heap, for our right half, it will be our 5. This is before I'm now covering how we are adding 3 element here. In order just to cover this, how we handle handle this edge case. So since 3 is less than maximum value of left half, is belong in the left half. First, we will just adding here elements, and so we added. We still have our 4 on the top, and right half is doesn't change. After adding 3, we notice that rule 2 in here, the heap should be equal size, but max heap can have one more element than min heap. So yeah, this observation help us define the 2 rules for managing the heap. This is what I told you. The maximum value of the max heap with left half and min heap. So basically these 2 rules, which is we are going to apply into algorithm, which is I just told. So you can find it here. After adding 3, we notice that rule 2 has been volatile. Since the size of left half heap is more than 1 element larger, Then the right half heap we can fix by moving the max value. So what we do, we have this 4. We know that it is maximum out of our max heap, and we're just moving it here. So now our left half looks this way, and our right half looks this way. So to ensure the size of the heap, don't volatile rule 2, we need to rebalance the heap after adding a value. Yeah. 1 second. This not this example. It's this example. Seven, 8, 9, and 5, and here 2, 2, 1. Yeah. So now the sizes is equal. Is it clear? This I bring some examples in different to cover the different cases. So, for example, you're maintaining your house, and as we discuss just this example, at some point your left half size is bigger than right. You just need to pop one element from the left and put it into the right. And this the opposite example. So for example, at some point, your right half is bigger than left on one element, but we know that our left half is actually should be on one element is bigger, means it's again volatile, our second rule. We're just moving from right to left. And that's in this case, it will be balanced. And this case is also balanced. So that's it about the algorithm, and this the code. At the beginning, you just need to create your heaps. One is max and one is min. Next, on the add elements, what you're doing, you're just adding your elements here to max offer, min, max poll. You're adding just 1 second. Here will be 1. Heap is never smaller than min heap. And you're adding here 1. Then we have 2. Okay. So we take this example. Let's do some dry run. So first elements will come here. We add, it's our max now containing 0. Here. Next, what we are doing, just to check code should be correct. We poll, we put it here, so it will be our min. We'll keep it 0. Max won't have it. Next, we are checking max size less than min size. It's not true. And here we will add our 0 element here. Yeah, this this is something which is you when you will implementing, you need to make the dry run to understand. It is not like very straightforward as I discussed on the iterations when we are adding, and it is reframe for us, but there is will be required some dry run to make. So we have one next, and now we have max here. It will be like this. Next, what we are doing, max poll element. Putting one, the top should be I think it should be one. That should be, it's max and min. Max offer nums will be 0. The rest will be min elements. I think it should be 1, right, folks? We are polling and we're taking 1. And our min should have 1 at this point. But again, we are this will be 0. Max size and min size. Then our 1 will go here. Next, we will add 0, 1, and 2. Min again will be empty. We will put 2 here. And next, max size. No, max size is still, max size is not smaller. We will put here 2. Okay, yeah, gotcha. Understood. So, folks, is not clear, right? This part. Not clear. I will explain now. Yes. Our min heap at the beginning should contain the biggest one. That's why we are all things doing here like this. It's a little bit confusing. I don't know if it's confusing you, but it is just confused me while I did it, the dry run, in order to understand why we're doing this way. So this is the trick. We're doing our max here. We're maintaining, so we're supposed to have the largest element on the max for our left half. But actually, this is the largest element for our left half, should be the smallest element for the min heap, which is we are keeping on the right. What we in order to maintain this order, what we are doing here, we're first adding to the left side elements. Means it is our max heap. All the time on the top, we're having our largest element. Then what we're doing on the next step, we are in our min heap, we're taking the largest element from the left half and adding it to the min heap. Don't be confused, min and max. So because at the top of min, there should be the minimum, the minimum value, which is actually will be maximum for max offer. That's why these steps over there. And this one is just to ensuring that heap size is the correct. So first things all the time we will add to the left half. On the left half, we will maintain on the top the largest element. What we're doing here, we are adding, then we are removing the largest element from the max, from our largest side, and we are adding to the min. Is it clear?
Livia, can I just ask a question? I think I'm just clarifying, but
Yeah.
so you are actually using a max heap on the left side and a min heap on the right side.
Yes.
Okay.
Yes.
Got it.
Yeah, and it is confusing. These steps are a little bit confusing. Why we are adding max first, and then next step we are pulling out of our largest element. So it's done for the reason because we as I explained it, our first our root element on the min on the right is actually the largest, the top largest element on the left. That's why what we are doing here, we are adding first on the left, and we're taking from the right side element, and then we're just ensuring if the size of actually of maintaining this order is the correct. Okay, and this simple check when we are finding the media. So you just need to compare the size. If size is equal, you're using this formula. If the size is not, you just pick the media element from your max heap. Or it could be min. There is no streak or advantages or whatever. So I also posted Python code here. How to deal it. Yeah. Any questions, folks? Okay. Then moving. This will be a little bit lecture at the beginning because we will deal with linked list. While we were dealing with linked list, we didn't cover this dummy node on the week, which is where for linked list we because we were covering the pattern fast and slow, and we cover a little bit terminology for linked list. But something which is also important to understand when you're dealing with linked list is what is the dummy nodes and why we need these dummy nodes. It's I posted when we need to have these dummy nodes, but it is also important to understand this concept when you're dealing with linked list. It's not specific to Heap, but as next task will be linked list plus Heap. So, and we will using dummy node, so it's important to understand. So now I'm going to cover this terminology. So handle edge cases cleanly. Most linked list problem involve adding, deleting, or modifying nodes, and special things happens if the head first changes. So removing the first node, inserting before the head, or returning a modifier and a new head. Without dummy nodes, you need extra logic for when the head itself changes. This clutters your code. By the way, everyone is familiar with linked list, with the week which we will cover. Okay. If someone is not, just raise your hand. I will explain what this head and tail. Okay, cool. So linked list, just will cover quickly because we have time. This is our linked list. We have elements, and we have reference to another element. This is basically what is linked list is. This 1 and 2 and, for example, 3. This is the data structure code linked nodes. Well, looks like this. It will be int value. And then you have reference, which will be linked node next. So this one, this structure, this is actually the object, and it is this node, where int is the value, and linked node next, it's the one for whom we have this connection with. So it's just a reference on the next element. And here we have, usually we have head. This is from where we are starting our linked list. And when we are moving, so you're starting from head, this usually a tail called, will be our tail here. So this is the concept. You in linked list, you always have head and you always have tail, but you have no idea what is in the middle. In order to find what is the middle, you usually traverse your linked list. I mean, because you have pointer, you are just changing this pointer. So for example, head, it will be our 1. In this case, head next, it will be our 2. That's how we operate with linked list. So we just traversing from the head till the tail, and tail usually pointed to the null. That's how we realize that we are at the end of linked list. Once there is no any elements and just null. So I hope this part makes sense. Yeah, please ask questions.
Sorry, thank you very much for explanation. I'm just new to Google Meets. I actually wanted to say thank you or something, but instead of that, I raised my hand. Thank you.
Okay, cool. Okay, so why we need dummy node? Most of the time we need dummy node when we're operating with head, because we have no idea if there is any other elements is present at any point of time. We have only knowledge about our head, and most time we're introducing our dummy node when operating on the first, when we need removing the first node, or we need inserting something here, or we need to operate on the head itself, or we need to make all this modification on the array list and return a new head. So we're introducing dummy head. It will be covered, folks. I will just briefly explain it. So simplify pointer manipulation. Why we need, as I explained it, you can live without dummy node, but it will significantly complicate your code itself. But it is not must have to have. It's something which just makes your code cleaner. And I will bring example where you can live without dummy node, and where dummy node is nice to have. This is basically everything what I just told. Now let's move. How does it work? How we usually introduce dummy node? So it is will be as I bring here data structure. What is this? It will list node. So you have this data structure. You just created one object of list node. It could be node, it could be list, whatever you want to call it. And usually we're using dummy, and you're putting value -1. For example, if there is no negative elements on the linked list, then you just create object with -1. Next, what you're doing, you're putting this dummy nodes. Okay. Somewhere should be example. So this is our list. This example, our head. And in the on this row, what will happen once you will introduce your dummy node? It will be -1, which will start pointing to your head. So basically, it will be the additional one node, which is will be at the beginning of your linked list. At the end, you just return the answer this way. So it will be, this is kind of code pattern which is always used, and you will see in the examples. Again, I explain it. It's just for pure how to implement linked list algorithms. So people figured out that instead of covering all the edge cases, it's easier to introduce dummy node, but it is very nice to understand this concept and used during the interview. But yeah, it is not like one must have. So let's look at this example. Here we need to remove I didn't put what needs to be done. So in this example, what we need to do, we need to remove, so basically what needs to be done, you have input, for example, it's just an example of one task where dummy nodes is useful. You have an input with the elements, and people, so in this task is ask, remove all nodes which is equal to. So at the end, it should be this one, which is output data, which is 3, 4, 5 without 2. That's what we are trying to solve in this example. With here's the code without heat handling. So what could happen? So just imagine you have this code. You ask. So is it clear? It's not very important, but important to understand from the code implementation what has been asked. I mean that we have data structure and we don't. We just need to remove our nodes with value 2. So and now we're going to implement it. We have our list node which is current. It's point to head. We introduce pref. So and we are going to work to modify this list. What can happen in this case? We found current value 2, which is true here at the beginning. This our head. It's pointed. We told that it is our current now, and this in while loop we're taking current value. We are asking if the value is equal to 1, which is we need to remove, and yes, it is. So this is how we're manipulating. It's probably not very clear, especially for those who didn't work with linked list. We usually introduce different pointers, and that's how we are going with manipulation. So the problem with this code that pref next at this point is null, and at this, because we are found our head. And it is 2, and we're falling down, and pref next we at this point is still null. If there will be free, for example, we will skip this step, and our pref, as you can see, will be pointed to current, and it won't be pointed to null pointer exception. But as we hit the case where head actually the one which needs to be removed, pref at this point is null. This is just a simple example where we're not handling it anyway at all our manipulation with linked list. I know it's probably for some folks are not clear because you need to have some practice on this. But let's just take a look what will happen if we will introduce dummy node here. So for example, we introduce the dummy node. Dummy now pointer to head. This is how it looks. We add our -1. Now that we're doing the same code, here, we're not hitting this case because we will first hit -1. We will have chance to point pref to the current. And then on the next iteration, we actually will hit where our head is 2. But again, you can solve this task without dummy node. How it will looks like. Instead of introducing dummy node, what you need to do, you just need first to move head forward if it needs to be deleted. So there is particular edge case, because this is edge case where head is actually a right away pointer to the value. And if we don't want to work with dummy node, we should handle this case by adding this code. So this all about dummy node. If you're not handling, there could be errors like null pointer exception we hit. One of the things which is people usually doing, they introducing dummy, which is pointed to the head, and they are error prone, and you don't need to care about any edge cases from the beginning for this particular task. If you don't want to introduce dummy node, you will just need to handle all the edge cases, which is you will encounter. Just 1 second, what I put here. Dummy works in linked list. Head is pointer to our original list. Dummy is the new node with any value of 1. What happens during the loop? You use, the summary. So this what we done in our code. So this dummy node, this is the head. We introduced it. We made some manipulations. Our dummy is currently pointed to a newly manipulated list where we remove our 2 values. And in the end, what needs to be done is just because we still have this node, we just need to return next, which will be pointed to our newly modified list. So just to sum up, it doesn't relate to heap. This is just some concept which we will use during the solving problem with heap, because we will dealing with linked list. This is a terminology which is nice to understand and nice to have. If you don't know this concept, during the linked list problem, as you're doing with any other data structure, you just need to handle edge cases. So this is all about. Is it clear, folks? You can walk through of this code and then ask questions. You can do some research or just ask on the Slack. Yeah. So now let's move then to our problem here. Okay. Now description. What needs to solve? You have combined sorted linked list. Given k singly linked list, each sorted in ascending order, combine them into one sorted linked list. So as an input, you have k single linked list. This our one, this first linked list, this second, and this one, the third one. What you need to combine them and preserve their ascending order. Is it clear from the description? There could be different number of them. It's not scoped to the 2. With 2 linked lists, it will be easier, but there is some different numbers. I believe it was currently, I think it's medium, but it was hard as well, a problem. So don't feel that you don't understand now something, folks. This literally very complicated topic, heap, because it's start to touching 3. this quantity once, and if you feel that you don't understand it, it's fine. Especially with touching linked list now, and with dummy node, it's make even more complicated. So just I don't know, ask questions on the Slack. Don't feel about yourself very bad. These two media and combining sorted linked list, it is a hard problem on the LeetCode. Do not expect that you will be asked for a general interview. During the a lot of companies, it's very specific questions which will be asked. Just because, folks, we're already on the 7 weeks, so expect that material is becoming more complex. We cover, I would say, Heap at this moment. It will be the last simple. It's not even simple because it's already using 3. But Stack probably was still not simple, but medium one. But now just material is becoming a little bit more complex and more advanced. So it is fine to not understand something, but please I encourage to ask questions, because this is the whole purpose of our lecture, to understand. And be proud of yourself, because we are hitting quite complex problems now. Okay, cool. So again, there is many solutions available. One of them use min heap. The simplest one will be just to traverse linked list, all the linked list which you have. This will be the brute force solution. If you will face this issue, this task, so the straightforward solution will be to take all the linked list which you have, to put them in the array, and then just sort this array. This will be the brute force solution, very simple one. You can write a way to give this answer. Okay, but one of the solution will be min heap. It's still not optimal one. There is a more optimal one, which is very advanced, as I discussed for top key problem. It's the specific sorting which is we used for solving this. Usually, you just mention during the interview that you can that you know this, but let me solve with min heap. Okay, let's see how it is, how it will work. Min heap, it's understandable, right? Why are we using min heap and not max heap in this case? Because we should preserve ascending order, right, folks? So at the top should be the smallest one. That's why it should be min heap, not max heap. If they will ask to have the opposite order, it should be max heap. But you will use max heap, but not the way how we're using min heap. But min heap we're using here, and we will adding only first elements from each linked list here. Okay. Just because we're dealing with linked list here, we will start from creating dummy node. Next, we will use min heap. This is our linked list. From each linked list, we will take the first elements from each linked list, and we will put them on the heap. Means min heap will sort them automatically for us, and at the top we will have the smallest one. So once we put them, we will take the smallest one from the heap, and we will assign to our dummy list. This will be our second iteration. Once we will assign first element, which is we remove from the heap, and assign to the list, this is our output, how we build it. We will take from the linked list another element, which is, in this case, it will be 6. We took our first, and we will put 6 back to our heap. Continue this until we have added each node from the all linked list to the output linked list. Once the heap is empty, we can return dummy next, which is head of the of the combined linked list. Why are we adding 6 here? I will explain how it's happened. So at the beginning, you're taking all your list, which is comes as in your input data. You're adding nodes to your offer. You're creating dummy list here. So means, as we discussed, the structure of our linked list. What you're doing here, so this one and this one 6. This one will be our heads. Oops. So this is our head. So at this point, as we know, it is not like array, right? When you're adding nodes, you're actually adding all this data structure underneath. Means you're pulling your node here from your heap, and you're pulling the whole this data structure actually. What you're doing here, to your dummy node, we are assigning 1 here. Next, next we're checking here. Not next is not null. It is we're checking if there is no null, which is assigned to 1. And if it's not null, then we are adding this 6, which is we're saying not next. For not next, this one is our 6. That's how we are adding here 6. That's what I mean here. So basically, you're putting all the data structure, all the list on the heap, kind of, because that's how a linked list is look like. Once you pop up your first node, because node is having reference on the next one, you are checking if it's null or not. If it's not null, then we're pushing here the next element from this particular linked list. And means on the next iteration, here will be 6, 1, and 3. We will pop up 1. We will add back 4 in this case. And next iteration here will be 6, 4, and 3. Next, we will pop up our 3, and we will add 7. Means here will be 6, 4, and 7. Is it clear? Yeah, it's just because we are dealing at this moment with linked list, where we're popping up our next node. So in the end, we built our dummy. We built our output list, which is pointed to dummy node first, and we are not returning usually, and we're returning the output, which is we built here. So yeah, basically this task all about. We're taking input list node, we're iterating, we're adding first nodes, which is our first heads. Next, while our priority queue or heap, while our queue is not, while our heap is not empty, we're popping up the smallest element from the heap. We are building our output, and here we are checking if next node is actually has any node. If it has, then we are adding to the heap a new element, and this will continue until we will hit to the end of each linked list. So basically, this is the whole algorithm about. Any questions? This is the end of this one. I believe this one I need to fix. Just will double check. This one I fixed, but yeah. So this one, the last one, which is I discussed, I fixed for Java. For Java, you can try to solve it, but I didn't fix for the rest languages. It's take array and returning array, which is not right. There's another task with similar to this one, but it is another one. So, folks, it's very silent today. No questions. I know it's complicated. Probably if you will ask questions, some questions, it will become clear, and not only for you, but for people on the phone. So I encourage ask questions, not today, but feel free to ask anytime. So, and you should be proud of yourself, because today we cover 2 hard questions, very hard questions. And top key problem is also very popular one. With Heap, it's very easy to implement once you know on this algorithm and know how to deal this with. So basically, it's all about using data structure, which is in your language, is actually Heap data structure, and yeah, just adding, and remember that it is in order. It min and max heap. So, and you just maintaining the size, and it's once you understand and know this algorithm, so it's very easy to implement. It's all about practice. This one, I would say, is very complicated. But still, yeah. Okay. Okay, shall then we're finish, folks. Do not expect that it will be easy next time. It will be even more complicated. So, yeah, go ahead, folks. Ask questions. You don't
Just
need
wondered, you mentioned the most optimized solution that you wouldn't probably have time for in the interview would be a sorting one. Could you just go over that again, please? Just roughly, sort of pseudocode style.
with the sort algorithm, with the one which is optimal one.
Yeah.
Yeah, I will post it on the Slack, 100%.
Thank you, Lily. Thank you.
No. Okay, thank you, folks. No other questions. I will share material on the Slack, whiteboard recording, and once I will fix the week 7. So, no. If you will struggling, just use code from whiteboard. If you want, I can post that code on the Slack, and you can debug, or you can just take a look and use them on the HackerRank contest. Okay, and have a good weekend. Bye.
Thank you. Bye.
Thank you. Thank you.